So what should be the running time for the quicksort algorithm? Intuitively, you might think both the merge sort and also the quicksort, they seem to be working in a very similar way. Namely, in the first stage, they have to somehow split the original list into left half and also right half. And then we have to individually recursively sort the left and right halves. And then you have to somehow either merge them or concatenate them. So they sound very similar. So since merge sort is actually in the worst case n log n, for quicksort it should be reasonably maybe also n log n. I would say that's only half true. The n log n for the quicksort only happens as a best case if you have chosen the pivot value wisely, meaning that the pivot value is very close to the median value for all the elements in the list. On the other hand, if you didn't really choose the pivot wisely, in that case, if you have chosen the pivot on a very extreme value, either on the lower end or the upper end, in that case, the resulting left half and also right half will be highly unbalanced. In that case, the overall running time will be surprisingly inefficient. That's something we'll actually see. Right? It's a very quick look ahead just to see what we're going to discuss about the running time. And let's do what we usually do. To really analyze the code line by line and then to figure out the running time. Let's do that properly. Quicksort is a very efficient sorting algorithm in practice, but you have to make sure the pivot has to be chosen very carefully. That's really the key of making the quicksort work efficiently in practice. We will go over bullet points on the slides about how the running time can be analyzed. At the same time, I'll show you the one-to-one correspondence to the code that we had. Remember, we got 1, 2, and also 3 different methods to implement the quicksort. We'll see the close correspondence in just a moment. Right, let's start with it. Let's start with the base case. So for the 2 base cases, either empty list or a list with only one element or singleton list, they both will just take constant amount of time to really sort. Well, basically no work to do. Right, that one's really straightforward. And you can see base case number 1, when the input list is of size 0, input size 1, both of them will be just returning the empty list or the singleton list. So big O of 1, which is the same as the case for the merge sort. And let's now go back to the recursive case. And remember, the first step is to choose a pivot elements. And for example, the rightmost element or leftmost or the middle one, but they're going to be very straightforward, which will take only constant amount of time. And if you go back to the code, that's exactly these 2 lines over here. Right, choose the pivot index and also get the corresponding pivot value. That's simply just constant, big O of 1. And let's go on to the next step. And to split the list into 2 halves, L and also R. So here I say unsorted, but in some way they have to be satisfying the following property. Every element in L must be less than or equal to the pivot. And also every element in R must be strictly larger than pivot, right? Even though they're unsorted, but you should really know the property they ought to satisfy. Right? That's exactly what I just meant over here about the left and right. And why would they be big O of n, linear? We have to look at the methods over here. If you look at the methods over here for all less than or equal to over here, and also all larger than, they simply would just have to go over the entire list and then decide conditionally which one might be either less than or equal to or larger than. So in the worst case, you have to go through the entire list to really check every element to see whether they should be included or excluded in the return list. So both of them should be big O of n. N being the number of elements in the input list, right? Every one of them. So this method over here, not surprisingly, is big O of n. And this one over here, to figure out the second half, will also be big O of n. Right? Let's now go back. So you can think about this part over here, this part over here. To really get the left and also right, each one of them is going to take big O of n. Combining them together will also be linear. So big O of n over here. Right? Maybe I can write a little bit better. So this part over here, big O of n. Right, let's now move on to the recursive part, where we're going to make a recursive call. So we have to recursively sort L and R. And how many times do we have to somehow split the L and R until we can reach the size of 0 or 1. Let's take a look at the tracing example we got earlier. You can see here, since we have chosen this value over here, somehow the split is more like an equal half and also half. So the resulting recursion tree over here is more like a balanced binary, well, it's more like a balanced tree, in which case the height is more or less like a log n. However, you may not be this lucky every time, which will result in the worst case. So that's something I want to warn you about. So whether or not the quicksort really performs well in the runtime really depends on how the pivot has been chosen, meaning that how balanced the left and right halves are really are like. So that's something I will also illustrate to you in just a moment. Right, so what you want to know is, in the best case, let me make a note over here. So when we try to do these two, sort left and right, okay, so you want to understand two things. Number one, the best case is pivot is such that the length of the L is more or less equal to the length of the R, more or less. Number two, the worst case. The worst case will be, I'm just running out of space, I'm going to put it over here. What's really the worst case? So for example, L is much less than R, or the length of R much less than L. Let me just give you one example. For example, let's say the L is simply equal to n minus 1, and then the R is maybe simply equal to 0, meaning that the pivot you have chosen has got all the remaining values less than or equal to that. However, there's no element that's larger than the chosen pivot. In that case, you simply got empty right half and also a linear length of the left half. In that case, it's going to make the number of splits that will be necessary for you to get to the base case much larger. That's something I'll visualize as well. But if you can already understand from my verbal remark, good for you. All right. Just remember to consider both the best case, which I'll highlight maybe in green, and also the worst case over here. Okay. Let's go back. And the best case will be just log n, because the two halves are pretty much like the merge sort. It's always going to split the two halves to be more or less equal to each other. In that case, the pivot should be close to the median value. That's something you may have you may be able to do for your algorithm. Right, and the last stage for the recursive step will be to concatenate the sorted L, pivot, and also sorted R. Right, so that would be basically this part over here. And this part over here is just about adding new elements into the list. And that one there, you can think about you're simply setting the next reference of some singly linked list for the left half and also the pivot and also right half. So it's really efficient, which will be just big O of 1. So all we have to pay more attention to elaborate would be exactly how the left and right are being split. That's something I would like to speak about. I want to speak about the best case versus the worst case separately for your full understanding about a quick sort. But so far you can see everything is certain except for how we do the split. Okay, let's talk about it. Okay, I think I got, yeah, so that will be big O of 1 just for the concatenation. So the running time for the quick sort, right, is going to be the running time for each recursive call. That one there is going to involve calling the less than or equal to and also larger than helper method. That's going to be big O of n for sure. That one's going to dominate. However, the number of recursive call depends on how many splits you would need in order for the left and right both get to the base cases. That'll be the numbers. In the best case, it will be log n. In the worst case, it turns out it will be linear. Right, so that's something I would like to tell you. And just note that this running time over here is really about the best case. It's not always the case. So one more slide to really go over about the running time. Let's say we do what we did earlier. We're going to denote, we're going to use a function t to denote the running time for the quick sort. However, it turns out there might be two scenarios for us to consider. let's consider one by one. The first case will be the worst case. And if the pivot, as I mentioned before, is such that the two halves, left and right, are very unbalanced. Just give you one extreme case over here. So let's say we always choose the rightmost element as a pivot, but somehow the input array or input list is reverse sorted. Can you picture that? How many splits would be necessary in order to get to the base case? Think about it. Right? Let's visualize it. So what we have is, let's say it's reverse sorted. Let's say over here, let's say this is my array. For example, I might have 9, also 7, and also 5, 3, and also 1. Reverse sorted, right? Well, mainly just about in the descending order, let's say. And let's say we always choose the rightmost element over here as a pivot. Once we have chosen this, what would be the left and right? Well, in this case, I think we only got just a right list, right? Because every other element over here is going to be strictly larger than 1. So what we get is we got empty left list, but we got non-empty. Well, we got all the elements, all the remaining elements belonging to the right. In that case, this is what we're going to get. We're going to get 9, 7, 5, and also 3. And let's say we chose the rightmost element as a pivot over here. In that case, again, we're going to get nothing that's actually less than or equal to the pivot, and everything else will be on the right. In that case, that's what we're going to get. We're going to get 9, 7, and also 5. Right? You can see the trend over here. Let's finish that to really make sure you are very impressed by this kind of unbalanced left and right. Right? Let's say we choose the rightmost again, 5. In that case, we're going to get empty left list, and also we got 9 and 7. Are we in the base case yet? Not yet. One more. Let's say we choose this one over here. After that, we still get empty left list, and we got 9. This will be the base case. How many splits do we have? The number of splits. The number of splits that's actually necessary for us to really get to the base case for this and also this will be 1, 2, 3, and 4. 4 splits. And the 4 over here is actually very, let's see, 4 over here. And how many elements do we have? We got 1, 2, 3, 4, 5. Basically just n minus 1, right? It's basically bigger of n. It's a very important insight for you to see for the worst case for the quicksort algorithm. Let me just recap very quickly. In this part over here, let me also highlight to really get to the sorted left and also sorted right. We have to ideally make sure the size of the left and right splits should be as equal to each other as possible. Hopefully proportionate or half and half. You will see some remark in the slide in a moment. But the worst case you don't really want to write into is when you got the extreme case like this. So every time you're only reducing the size of 1/2 just by 1. In that case, it will take exactly linear time for that particular half to get down to the base case with 1. So that's exactly linear time, right? And if this happened, so that means you will have to multiply the number of splits, which is linear, to the running time for each level for the recursion, in which case we're going to exactly create this right list, which will take linear time. So you got linear times linear, you got quadratic, n squared, which is basically just like insertion sort and selection sort. Right? Of course, this diagram over here just here to remind you, but let me just write it down for this example here. In this example over here, what we got is this left over here is only of size 1. And the right over here is actually much, much larger. Basically, all the remaining elements there. That one there will be basically bigger of n minus 1. Right? And can you actually derive the corresponding recurrence relation from there? Let's try. We know that for the base case, for the two base cases, it's simply just going to be 1 and 1. What about the recursive case? We know that for the left over here and also for the right, they are very, very unbalanced. It's like one of them is exactly just linear. The other one there is like a constant. So it would be T of, what's the input size? What the input size that's passed to the recursive call. For example, let's say for this one over here, entire size is n. And this part over here is 0. Subtracting the pivots, this part over here is exactly n minus 1. Right? That's kind of the worst case we have. N minus 1 over here. And then what else? At every recursive call, remember what dominates the running time. It would be this part over here. For us to really figure out the left and also right half. Even in the worst case where every element that remains turns out, every element that remains turned out to belong to the right half because they're all larger than 1. In that case, you still have to go over all of them to really put them into the right half. So that will still be linear. So this part over here is exactly linear. So that's why we'll say plus n. That's the recurrence relation for the worst case, for the quick sort. And it would be your exercise, which I'm going to put over here, to show what it is by unfolding. And I can tell you that it's going to be quadratic. In that case, it's going to be asymptotically equal to the running time for selection sort and insertion sort that we covered much earlier in the course. Solve the recurrence relation by unfolding. Right? So that will be your exercise. Make sure you do it. And let's now go back to the slides. And that's the recurrence relation I just laid out. And you want to really solve it, and it's going to be shown to be equivalent to selection sort and insertion sort. Running time wise, you'll be quadratic. Okay, make sure you do the exercise. What about the second case, for the best case? If the pivot has been chosen such that it is very close to the median value. Well, what does it really mean when the pivot is actually median? That means the number of elements less than or equal to the median, and also the number of elements larger than the median should be very equal to each other, right? The numbers should be basically the same. That's really the very definition of a median. Let's talk about the best case. The best case would be something like this. Let's say this is the original list over here, and if somehow you can choose the median value, right? Let me just okay, let's say this is the median somehow, and the consequence of that is the median value over here, by its definition. Well, of course, if you don't know what the median value is, you can look up the dictionary and or you reach out to me. The number of elements that's actually less than or equal to the median over here, less than or equal to, and also the number of elements that's strictly larger than the median, these size should be equal to each other. The size. Given that we can choose such median at every level of the recursion, how many splits do we need in order to get down to the base case? Well, it would be very similar to the scenario for the merge sort, because for the merge sort, we always find the middle elements and do the split, right? So what's going to happen is, given the original list, let me just give you some conceptual idea, and then after the first split, we're going to get about half for less than or equal to, and also about another half for less than or equal to, for larger than. So this will be n, and this will be n over 2, and this part over here is going to be n over 2 as well. And if you do another split over here, for example, this part over here, again, we chose the pivot so carefully to be the median. So this part over here and this part over here is going to be n over 4. N over 4. I'm talking about sizes, of course. N over 4 and also n over 4. And if this one here keep going until we want to get to only size 1, And this recurrence tree should be quite familiar to you, right? So how many splits do we need overall? It should be log n. This part over here should be log base 2 n. Right? That would be the heights. How many splits that would be required? Alrighty, let's now fill out the recurrence relation. What's going to happen is we're going to have the same base cases, which would be 1 and also 1. And don't forget, they are simply just over here. Just for completeness, I'm also going to annotate it. Big O of 1. And we know that this part over here is also going to be big O of n. This part over here, big O of n. And what about this part over here? The sorted left and also sorted right. Given that it's the median value is actually chosen for every pivot. So what's going to happen is we're going to get T of n over 2 for the left and for the right. So that means we're going to say 2 times, right? One for the left and the other one for the right, because they're always like an equal split based on the pivot that we have chosen close to the median. And then we also need to include the linear work over here to really split them using the less than or equal to and also larger than methods. That will be the recurrence relation. And this one here is exactly identical to the running time recurrence relation for the merge sort. And of course, you can do as exercise to try to unfold this. That's something we did earlier. And this will be also your exercise to solve it by unfolding. And you can expect to get n log n for the best case. Okay. Let's now go back to the slides over here. Right? That's a recurrence relation, and as it will be as efficient as merge sort. And let me tell you some look ahead. For this final week, we're also going to cover a final sorting algorithm based on a heap data structure. It's called a heap sort. Turns out, heap sort is also n log n asymptotically. So overall, we will have already learned 5 sorting algorithms for this course. Let me recap them very quickly. We got selection sort, insertion sort. They are both quadratic. And also we got merge sort n log n. We got quick sort, which can be either quadratic or n log n. Also we got the heap sort that we're going to learn after this recursion lecture about the heaps. That would be a heap sort, which is n log n. And one thing to note, when we say we want to really get the median value, it doesn't necessarily have to be exactly the median. As long as the splits can be somehow proportionate. For example, even for n over 10, 9n over 10, it will still be n log n. So what you can try is as follows. Okay, you can try an extra exercise over here. Let me put it here. So we can say T0 equals 1, T1 equals 1, and also we say Tn equals T of n over 10 plus T of 9n over 10, n plus n. You can see here n and also 9n. So they are proportional split, even though not exactly like a half and half, which is okay. As long as they're proportionate, that's fine. This will be your extra exercise. Right, let me just highlight it. So this part over here, exercise number 2. Exercise number 1 was over here, and also you got exercise number 2. Okay, let's now go back. And that's it. So now we are done with the recursion lecture, and notice that we actually split this single lecture over many weeks with the intention that it does take time for you to digest each of the ideas that we spoke about recursion. So there are background study for you to do, and also there are more intermediate problems that we actually discuss about the recursion. So that's why I want to split it over weeks, so you can actually don't have to study them all in 1 week. And there's one notes which I made for my earlier course over here. You can take a look. It does summarize about the recursion solution pattern that are actually very common for programming recursively. And also, this will be my final advice. Even though we have gone over so many extra problems and also the example in the lecture, but the best way to learn about recursion is to really program with the so-called functional programming language. That's always the advice I give to my students. And there is one language that's very fun to really learn and also program with called Haskell. It's a functional programming language. So for those of you who might want to do something extra in the summer or to learn something on your own, you can definitely go to this link over here will be as a starting point to learn about the functional programming language, where recursion is simply the first-class citizen objects, right? Just have fun with functional programming. That will definitely help you learn about recursion for your future endeavor.